Hello, welcome to the course Mathematical Foundations of Computer Science. In this lecture, we are going to study about the concept of propositional logic. So, let's see what is the importance of this course or this concept propositional logic, why we have to study this, and what all concepts we are going to study in this course. So, this already we have seen the syllabus of our course. Unit 2 is mathematical logic. This is the propositional logic concept. So, we are going to study about propositions, logical operators, equivalences, implications and connectives. Along with those, we have two more concepts, PCNF and DCNF. So, people from electronics background, if you have studied the course digital electronics or digital logic, then this course is just a cakewalk for you because lot of concepts are similar to your digital logic. Why we have to study about proposition logic? Before we go to this concept of proposition logic, let's understand what is a proposition. What is a proposition? Any declarative statement which is either true or false but not both is called a proposition. Any statement which is either true or false. For example, if I say today is a rainy day, it's a declarative statement. If I say that 2 plus 3 is 5, it's a declarative statement. It can be true, it can be false. If I say Hyderabad is the capital of Tamil Nadu, this is also fine because it's a declarative statement, but it is false. So, this is a proposition. Let's see what are the important, why we have to study this course, what is the importance of this course. So, propositional logic is also known as proposition calculus, okay, or sentential logic. It's a branch of logic that deals with propositions and their relationships through logical connectives. So, we have to study three things here: propositions, logical connectives and the relation between the propositions. So, it is used to reason about algorithms and their correctness. You see, propositional logic is widely used in algorithm design and analysis techniques. Here what we do, see, when you write a program, when you write a program, we have to validate whether the program will give the expected output or not. In such cases, we have to convert that program into a mathematical format and apply some mathematical techniques, check whether it is giving the expected output or not. Okay, so when you are verifying or correcting a program whether it is giving an expected output or not, we use proposition logic. Also, it is used in functional programming. Functional programming is a type of programming which very rarely exists these days, but still we use this propositional logic concepts in this functional programming. Yes, obviously this concept of propositional logic is very widely used in AI, specifically in reasoning and problem solving. So it is used in data science as well, which is part of AI again. How is this used in data science? See, when you have data with you, you make some decisions on that data, you make some comment on that data, you call those comments as hypothesis. To test the hypothesis whether what you have said on the data is true or false, we have to use propositional logic there. We try to convert that hypothesis and conclusion into mathematical form and prove or disprove whether the hypothesis or the comment made by you is true or false. Obviously, it is used in natural language processing and also in digital circuit design. So, wherever you want to make some decisions, you want to make some choices, make some conclusions, we use this proposition logic. So, this is different fields of computer science where this course or this concept is used. So, these are the contents or syllabus of this unit, proposition logic. We have to study about propositions and operations on propositions. So, we have different operators here, and then we will see truth table and logical equivalence, operator precedence, loss and PCNF, PDNF. Let's try to begin with proposition. Proposition is a declarative statement which is either true or false but not both. It's a statement which is, that's why I said it's a declarative statement that is true or false but not both. Let's see. Example: Washington DC is the capital of USA. It is a declarative statement. It can be true or false. Delhi is capital of Canada. It's a declarative statement. It is false, but it's a declarative statement. So all such statements are called as propositions. 1 plus 1 equal to 2, 2 plus 2 equal to 3. All these are propositions. Okay. So if you see this kind of questions, like what time it is, it's not a declarative statement. It's a question. It is not a declarative statement. So in this case, we say this is not a proposition. Read this carefully. This is also not an declarative statement. It's an instruction. It is not a declarative statement. So this is also not an proposition. See, x plus 1 equal to 2. X plus 1 equal to 2. Then we have another statement, x plus y equal to z. See, these are neither true nor false. These two statements are neither true nor false. So they are also not the propositions. So how do we use propositions? Generally, when you have a plain text, plain English language statements, we try to convert that into mathematical notations. For that, we use some conventional letter format, that is PQRS. We'll be using that. And for every proposition, we have seen just now that a proposition can be either true or false. So if it is yielding a true, we denote it by T, and if it is yielding a false, we denote by F. And the table which contains these true or false values is called truth table. Always it is called as a truth table. Though the name is truth, but it contains both true and false statements. But those tables are called as truth tables. So the area of logic that deals with proposition is called proposition calculus or proposition logic. And sometimes you have to combine multiple proposition statements. Such kind of combined statements are called as compound propositions. Okay, they are formed from existing propositions using logical operators. So we connect or we combine two different proposition statements using different logical operators. So what are the logical operators? It can be negation, conjunction, disjunction, implication, and bi-implication. So let's study about these logical operators. First one is negation. It's very simple. If P is a declarative statement, then its negation can be minus P or P bar, or we can write like this. P. We have different notations. So if a declarative statement P is Ramu is a good boy. If this is a declarative statement, it's a proposition. Its negation P will be Ramu is not a good boy. So we have to include not here. So this is about negation. Its truth table is very simple. Let's see the truth table. So that's what negation of P is denoted by this symbol or P bar. It is not the case that P. Its meaning is it is not the case that P. So truth value of negation of P, that is negation P is the opposite of truth value of P. Let's see the truth table here. See, if the value is true, its negation is false. If the value is false, its negation is true. This is simple. And some example, 2 is positive, its reverse will be 2 is not positive. Example 2, Vinay's phone has at least 32 GB of memory. Its negative will be does not have 32 GB of memory. This way you can do all these exercise problems. You can convert this into negation statements. Next, conjunction statement. So in digital electronics, you know about AND operator. AND gate or AND operator you might have heard about, right? So our conjunction is about AND operator. We represent it using reverse V. So what is this definition? Let us see. If P and Q are two propositions, then the conjunction of P and Q denoted by P and Q is the proposition. See, we write it as P and Q. We call it as P and Q. So what is the point here? P and Q is true when both P and Q are true. In all the other cases, it is false. Only when P and Q are true, the final result is true. Otherwise, remaining all are false. So, see, note that in the logic, the word but also appears sometimes instead of and. So, this is also called as P but Q. Okay, sometimes but is also used instead of and. So, the example you see, the sun is shining but it is raining, or I can say the sun is shining and it is raining, both are same. Truth table, if you observe, that's what we said, only when both are true, the result is true. Remaining all the cases, the value are false. It is false. This is your AND operator, also called as conjunction. Let's see some example. See, proposition P, 2 is an even integer. Q, 7 divides 14. What is P and Q? 2 is an even integer and 7 divides 14. That is the conjunction statement, combined statement using AND operator. Like this, we have multiple examples. You can go through and see how conjunction works. Next is disjunction. It is equal to your OR operator. We use the symbol V. So we write P or Q this way. We call it as P or Q. So when you have two compound propositions, we use OR operator. Okay, that's what it is saying. See, P or Q, like this. So what about this? P or Q is false only when both are false. Remaining all cases, it is true. Okay, it is reverse of that. Okay, P or Q is false only when both P and Q are false. It is reverse of our conjunction operator. Let's see the truth table. See, true, true, the result is true. True, false, the result is true. False, true, the result is true. Only when both are false, the final answer is false. So it is simple, adding an OR word, keyword OR in between two statements. Let's see example. P, 2 is an integer. Q, 3 is greater than 5. So you see, P or Q. P or Q means 2 is an even integer or 2 is a greater than 5. Okay, this is not 3, this is 2. 2 is an integer or 2 is greater than 5. Just include OR symbol in between. Like this, you can see different examples and try to solve it. The third important operator or the fourth important operator is implication. Implication. This is one of the very important propositional logic operator which is used widely in problems of computer science. So implication, it means we use the symbol P implies Q. This is read as implies. We say implies. P implies Q is the proposition, and the plain text way of writing is if P then Q. It is if P then Q. Okay, so Q can happen only if P, right? So what about this? P implies Q is false when P is true and Q is false. In all the other cases, it is true. Only when P is true and Q is false, the final result will be false. Rest all other cases, it will be true. So in the conditional statement P implies Q, P is called the hypothesis and Q is called the conclusion. So this is called implies. So different forms, this is very important. How do we call this statement P implies Q? It can be called as P implies Q, P is sufficient for Q, Q if P, Q whenever P. These are different forms of the statement implication. Truth table, if you see, that's what we are talking about. Only when one is true and the second one is false, it is false. Remaining all the cases, this is giving true. This is about implication statement. And this slide is very, very, very important slide. Okay. This is very important slide because this P implies Q can be interpreted in different ways. Let's see what is this. One way, the standard what we already seen, if P then Q. Second, if P only Q, there is no then keyword, but still it means it is P implies Q. Third one, P is sufficient for Q. It also means P implies Q. These are all different terminology in plain text of English we use to represent P implies Q. See, reverse. Q if P. Same thing. This we are writing in reverse. Here it is if P, comma Q. This Q we bought it here. It is Q if P. Okay, that way. Next, Q when P. P implies Q, normal standard one what we are talking about. P only if Q. See, P only if Q. And a necessary condition for P is Q. A necessary condition for P is Q. A sufficient condition for Q is P. Understand this. A sufficient condition for Q is P. Q whenever Q is necessary for P, Q follows from P. So these are different ways we have, we represent terminology to talk about P implies Q. Why we are studying this? Because sometimes we will be given a English statement which you have to convert that to mathematical logic. That time you should know which one to use here. We will see some example exercise problem so that you understand it better. Examples of implication, you see, P, Rahul learns discrete mathematics. Q, Rahul will find a good job. You have two statements here, P and Q. Express the statement P implies Q as statement in English. So how to do that here? If I know the basic case is, if P then Q means P implies Q. So if you see, if the answer is, if Rahul learns discrete mathematics, then Rahul will find a good job. So just include if in front of this statement and then in front of second statement. That will give the answer. Okay. So if Rahul learns discrete mathematics, then he will find a good job, or Rahul will find a good job when he learns discrete mathematics. This I wrote like this: Q when P. I use this here, Q when P. So there are different ways. Okay. So you can see some other exercise problems. In implication, we have three different kinds of statements: converse, inverse and contrapositive. For there are three types of statements in implication, P implies Q. What are those? Converse, inverse and contrapositive. Let us try to understand what are these statements. So if there is a conditional statement P implies Q, we can form different forms of statements. Converse means Q implies P. Inverse means minus P implies minus Q. And contrapositive means minus Q implies minus P. Okay. Converse, if P implies Q is a statement, converse will be Q implies P, inverse will be minus P implies minus Q, and contrapositive will be minus Q implies minus P. Okay. So sometimes in exam you may be asked some question like this, given a statement like this. It's a conditional statement. If it is raining, then the home team wins. Means you write here like this: P, it is raining. Q, home team wins. So this is what we are given, P implies Q. What is converse for this? Converse is Q implies P, means if home team wins, then it is raining. If home team wins, then it is raining. What is inverse? If it is not raining, then the home team does not win. If it is not raining, then the home team doesn't win or does not wins. What is contrapositive for this? Contrapositive is negation P. That is, if home team does not wins, then it is not raining. If home team does not wins, then it is not raining. So you have to understand what is P, what is Q, and just write the statements based on these equations. Okay. So these are different solutions. And the last operator is biconditional operator. Biconditional operator statement means P double implies Q. In the previous case, he has been only P implies Q. Here it is P double implies Q. So how does it happens? So if there are P and Q are two propositions, the biconditional statement P double implies Q is the proposition P if and only if Q. It is P if and only if Q. Okay, if and only if Q. That is very important here. So this is also called as by implication. So we can use either IFF or if and only if, or P is necessary and sufficient, both condition for Q. Truth table, if you see, this is same as your XOR operator. It is same as your XOR operator. See, when both are same, it is true. When both are same, it is true. Other cases, it is false. Okay. When both are true, it is true. When both are false, it is true. And when it is one is true and other is false, both is false. Okay. When both the values are same, it is true. Remember that. So let's see some example. You can take the flight, you can buy a ticket. We are asking you to write what is P double implies Q. So you can write, you can take the flight if and only if you buy a ticket. That is your P double implies Q, or okay. That way we can write, see, you can take the flight if and only if you buy a ticket. So let's see two example problems, the problems which we can expect in exams. You will be given two propositional statements. You have to convert each of these expressions into English sentence. For example, you see P implies Q. What is the statement here? P, I bought a lottery ticket this week. Then Q, I won the $1 million jackpot. So what is this P implies Q? If I have bought a lottery ticket this week, then I won the $1 million jackpot. Then I will win the $1 million jackpot. If and then you have to include here for P implies Q. Okay. What about P and Q here? Simply put and. Simply put and. So you have to write like this: I bought a lottery ticket and I won $1 million jackpot. Like that you have to write. You see G, negation P and negation Q. So if I have not bought a lottery ticket this week, not if, sorry, it is negation P. I have not bought a lottery ticket this week and I have not won the $1 million jackpot. That is your G. So this way you will be given expressions, you have to convert them to plain text of English. So this is the solution for that, for these problems. You can note down these questions and you can then compare the answers with your solution. The second kind of question is, you will be given two proposition statements P and Q, and you will be given plain text in English language. You have to convert them to mathematical logic. You have to convert them to propositions. See, you drive over 65 miles per hour. The first question is you do not drive. It is negation P. See, here it is if and then. It means there is some implication, but it is if you do not drive, then you will not get. So answer is minus P implies minus Q. That way, given plain text of statements, you have to convert them into mathematical logic. Okay, see, driving over 65 miles per hour is sufficient for getting a speeding ticket. It is nothing but it is P is sufficient for Q. Here it is given as is sufficient is used. So we have to write here P implies Q. Okay, for this one, this is P sufficient for Q. So it is Q implies P. Why? The meaning of P implies Q is Q is sufficient for P. So here driving means this statement is given as P. Therefore, the value will be Q implies P, reverse of it. Okay. So this way you have to, you can see the solutions here, right? How, that's what I was talking about, P implies Q. So you have different English statements, you have to convert them into propositional logic like this, using those logical connectives. Okay. So in this discussion, we have studied about propositional logic, why is it important, what are the different operators in propositional logic, and how we try to solve the problems by given a plain text, converting them to mathematical logic. Given a mathematical logic, how do you convert them to plain text? Okay. So in next unit, in the next lecture, we will try to see about the truth tables and the different problems on them, and also about PCNF and DCNF. Thank you.